So we're going to start with the method of joints, which is section 6.2. So for the method of joints, we basically take the joints and we do our force analysis there. So we use our equations of equilibrium. And we'll just take out, so say we're interested in what's going on here, we'll look at this B. So this is just the joint B. And so what forces do we have acting on it? We have this 500 Newton force, and then we have the force from B to A, and then the force from B to C. So that would be our free body diagram. We have a 45-degree angle there. We're assuming that the force from B to C is in compression, and we're assuming that the force from B to A is in tension. You could make either assumption, and it'll work itself out. But then basically the steps are, then you just sum the forces in the x direction equal to 0, and we can sum the forces in the y direction equal to 0. So if we want to do this one, which we can basically, let's sum the forces in the x direction equal to 0. It's like we forgot our x and y. So positive x and positive y. We basically get 500 newtons minus FBC times the sine of 45 degrees equals 0. And so basically we get FBC is equal to 500 newtons over sine of 45 degrees. So just pull my calculator out. Then we get 707 newtons, and then we can sum our forces in the y direction equal to 0, so our second equation of equilibrium, and we get negative FBA plus that FBC, which we found out to be 707 newtons, and because this came out as positive, that means the direction we picked was right. So plus 707 newtons times the cosine of 45 degrees. That equals 0, so then we get FBA is that 707 times the cosine of 45. Which is 500 newtons. So with this method of joints, we can basically just move throughout a truss. A lot of times the trusses are more complicated than this, but you might start with one, then move to another, and then another, and you can figure stuff out. I guess the other important thing that I should have said is that typically when we look at the first step is typically we'll figure out what's happening at these two ends, so the support reaction. So typically the first step would be to draw a free body diagram of the entire truss. So for this one, we have this triangle. We have at A, we have a pin, so we'd have an AX and an AY. And then at C, we have that roller, so we just have CY. We have that 500 Newton force. And then with this, we can sum the forces in the x direction equal to 0, sum the forces in the y direction equal to 0, and sum the moments about a point equal to 0. And I'd probably pick A just because that's the one we know the least about. So if we sum the moments about A equal to 0, we'll be able to get CY. Once we have CY, we can sum the forces in the y direction. Then that'll give us AY. And we can, I guess you could have just looked at it to figure out the only force in the x direction is AX. So AX is actually going to end up pointing, so we would have picked wrong had we done that, but it'll end up pointing that way because this is the other force in the x direction. So I'm just going to quickly write down the steps for analysis. So the first step, if you don't know the support reaction, so if those aren't given, you want to draw a free body diagram of the entire truss to determine the support reactions. So typically, and that's what we had just done, some of the forces, in the x equals 0, sum of the forces in the y direction equals 0, and the sum of the moments about some point equals 0. So typically we can use those three equations because we're just in 2D, and we can figure out the support reactions. One thing I didn't mention, I don't think I'd mentioned earlier, a lot of times these trusses, they'll have a pin at one side, and then on the other side they'll have rollers. And if you think about it, the reason that they have rollers on one side is because in the case of a roof or a bridge, a lot of times you'll have expansion or compression depending on the weather and the temperatures and stuff. So with the rollers, it can actually move a little bit that way or a little bit that way, and take into account, instead of if it was fixed, then you would be putting those members in compression whenever it expanded or whatnot. So a lot of times you'll have rollers on one side and pins on another. For step 2, you want to draw the free body diagram of a joint with one or two unknowns. So typically that'll be starting from one end of the truss. So if you've already figured out the reaction forces here and here, you might start there, depending on what you're interested in. And then you want to assume that all unknown member forces are in tension, so basically pulling on the pin, unless you can determine by inspection that the forces are compression loads. Sometimes you can look at it and figure it out. In that case, it's okay. Then for step 3, you want to apply the scalar equations of equilibrium, sum of the forces of x equals 0, and the sum of forces of y equals 0 to determine the unknowns. If the answer ends up being positive, then the direction you assumed is right, and otherwise it's in the opposite direction. Note that because we're doing joints here, or this method of joints, that we can't sum the moment about any point equal to 0. That doesn't work because we have no moment arm, so that equation doesn't help us. So we can basically deal with members that have two unknowns. For step 4, you basically just repeat steps 2 and 3 at each joint in succession until all of the required forces are determined. So you'll just move in that truss. So say we started with this joint, we figured out these forces, then we can move down to this joint. So we already know that one. So we already know that one. And then we just have two unknowns here, so we can find those out, and then we can keep moving through it. So move it maybe up to there next, and then down to there, then over to there, until we get all the required ones. So now we're going to talk about zero force members. This is still in section 6.3. So for zero force members, this is one of the things that'll help us with doing it by inspection. But these rules will sort of make your life a little bit easier. So we'll be smarter instead of doing harder ones. So it's good ones to keep in mind. Basically with this, if only two members form a joint, so if only two members form a joint and no external load is applied, then both of the members are zero force members, which that's just ZFM, zero force members. The second rule is, so if the three members form a joint and two are collinear and no external load is applied, then the third member is considered to be a zero force member. You really want to look for these. They'll make your life a lot easier. I'm going to show you two pictures just to show you what I'm talking about. Visually it may make it easier. So for the first one, if you only have two members form a joint and no external load is applied. So let's look at this truss and see which ones that works for. So if only two members form a joint, so right here we only have, there are two members, 1, 2, so DE and DC, and there's no external load applied, so then both of those members are zero force members. So this is a zero force member, and this is a zero force member. And then, let's see, that one had, this, at E, we've got 1, 2, 3, 4, so that doesn't work. We have 3 at C. We have 1, 2, 3, 4 at B. At A, we only have 2. And no external load. So at A, these would also be 0 force members for both of those. So when we're doing the analysis, we can actually basically just get rid of those 2. So that was where that joint A was. This is where that joint D was. So you can see that really simplifies it and makes it easier. So for the next rule is if 3 members form a joint and 2 are collinear and there's no external load applied, then the third member is a 0 force member. So now we'll look at an example of that. So for this one, so let's look where we have 3 collinear, or 3 members for a joint and 2 are collinear. So let's look at D. So we have 3 members, and DE and DC are in the same line. That's that collinear. Then we have a third one. And there's no external load applied. Then this member here, that DA, is just a 0 force member. So we can just take that one out for the analysis. And then we have it again at joint C. We have these 2 members are in the same line. They're collinear. Then we have this third one. No external forces. So this one also would be a 0 force member. So we can basically rewrite that joint to look like this, which you can imagine is a lot more simple. So those are good things to think of, and so that you can sort of do them by inspection, which was our third method. So for those 2, for the 0 force members, basically that gets into that by inspection method, which was that third method that we talked about for solving these equations. Sometimes you can do this depending on the setup, and basically it's whenever the members, when you can figure out the internal forces without having to take a joint or do a section cut and do the equilibrium equations. And so just make sure you keep an eye out for 0 force members. And I guess the last thing for the 0 force members is the reason that why you would even have 0 force members in a truss is basically to aid in 0 force members. They help you aid in stability. And any changes in load. So stability, things like buckling. And for changes in load, things like wind, cars, that sort of thing. And you've all probably seen the video of the bridge that the wind started going, it hit the natural frequency, and then it fell down. So that's the reason why you would have these 0 force members, are to help with some of that stuff. So make sure you keep an eye out for those. Sorry this is such a long video, but does a lot with trusses. So the last section for trusses is the method of sections.